This idea of vectors. Remember, we've been talking about the translation of graphs, and I guess that's why we look at that topic before this one, because there is actually a direct relationship with the vectors. If we'd had this question, we've got the parabola x squared, we're going to translate it 2 units to the right, and then we're going to shift it up 1 unit. Find the new equation. So here's our original parabola, we're going to shift it 2 and up. There's our new parabola. We could say, well, we know the x squared, we've shifted it right, it becomes x minus 2 squared. Then we've shifted it up, it becomes x minus 2 all squared plus 1. Okay. Now look, we did that using 2 shifts, one horizontally, one vertically. I could combine those 2 translations into one single translation, into what we call a displacement vector. There it is there. It's the hypotenuse of that right angle triangle, if you like. Now, the beauty of using vectors is I can move vectors anywhere I like, as long as I'm just sliding it, and its length is never going to change, and the angle it makes with the horizontal doesn't change. So all I'm doing is sliding it. So I could pick any point on that parabola and slide that vector to it, and it would go to the other parabola. Doesn't matter where I put it. Pick any point, it'll go to a point on the other one. I could write it like this new parabola, so I don't confuse my pronumerals. I've made them capital X and capital Y. I could say, hey, it was the original ones, but look, I've added to the x values, I've added 2, and to the y values, I've added 1. We've shifted it that way. And these are what we call vectors. But now I could think about it like parametrics. So instead of calling it x and y, I'll put it in parametric form. I'll call the x value t, the y value becomes t squared. And so now I know capital X is t plus 2, capital Y is t squared plus 1. What is the equation of the new curve? Well, using our parametrics idea, I'll make t the subject in the x one, I'll substitute it into the other, and there's that equation that we worked out before. So some definitions. So what I was just talking about there is what we call the displacement vector. Now the notation is quite important. PQ, and then we put the arrow on top, and that's telling us the direction of the vector. We're going from P to Q. That's what we call a displacement vector, going from P to Q. P, we often call the tail of the vector, Q, the head of the vector. There are other notations for vectors that we use. Sometimes we just use the pronumeral, but it's bold. Not a great one to do when you're handwriting, because it's hard to make sure, oh, this is bold. What do? You go over it and over it and over it, but you could still misread it. So we tend not to use that one when we're handwriting. We use this one instead, where we put a tilde underneath it. So it distinguishes between what is a vector and what's just a pronumeral. But as I was saying, all of those vectors can be identified by their length or magnitude and the direction it makes with that horizontal, that angle, which is in line with what we saw in coordinate geometry, I guess, why when we're finding the slope of a line, we say it's the tan of the angle, but it's the angle that it makes with the horizontal. It's all the same idea. So the magnitude, which I simply just use the absolute value sign, because remember, absolute value just means what's the size, I don't care about the direction. Absolute value could be P with a tilde underneath, or I might say the actual vector itself, PQ, but we're talking about how big is this vector, what's the magnitude of the vector. Opposite or negative vectors are just in opposite directions. So if I'm saying the vector PQ and I'm representing it with P with a tilde underneath, then the vector QP would be negative P. It's going in the opposite direction. Instead of going from P to Q, it's going from Q to P. Parallel vectors will have the same slope. It makes sense. It's sort of like parallel lines, isn't it? But we're talking about vectors now instead of lines. The vector PQ would be parallel to the vector QP. It's just they're going in opposite directions. They would actually be parallel. They might even be the same line in some cases. Then we have this thing called the zero vector. This way I've written it here is probably the more unusual way of writing it. So we're saying PP. We're going from P to P. We're not going anywhere. It's nothing. The other way, probably more common to write the zero vector, is simply writing 0 with a tilde underneath it to highlight, yeah, I'm talking about 0, but I'm actually talking about the 0 vector, not the 0 as a number. A scalar is magnitude that doesn't have direction. So it's not a vector, it's just a real number. It's just some number. So we see something like this, lambda times p with a tilde underneath it. Well, then we know lambda is the scalar. It doesn't have a tilde underneath it. It's just a number. as opposed to P, that's a vector because it's got the tilde underneath it. That's why it's so important. Don't neglect the tilde underneath the vectors, otherwise people might get confused. Are you talking about a scalar, or is it the vector but you forgot to put the tilde underneath it? That's quite important. So it would be in the same direction, because the scalar doesn't have direction, so it's not going to affect the direction, it's just going to affect the length of it. And it will end up being lambda times whatever the length of the vector P is. That'll be the final length. Now, a position vector as opposed to a displacement vector. A position vector is a special type of one. The tail is the origin. So any vector where the tail is at the origin is a position vector, not a displacement vector. So how do we play with them? Adding and subtracting of vectors. We add them by placing them head to tail. You put the tail of one on the head of the other. So if I've got this vector A and I want to add this vector B, then there's the first one. I'll add to it the second one. So you're just adding it onto it. The result is, if I said instead of going along A and then along B, what about if I just went straight from the tail of this one to the head of the other one? That's the new vector. That's the vector A plus B. And it's commutative. It does commute. Because if I went B and then I went A, alright, draw B in, then A in, we get the same vector. Okay, I might call it B plus A instead of A plus B, but again, addition does commute. You can do it in any order. Another way of expressing that, I can say, I'm going to get the vector PQ, there's PQ, I'm going to add the vector QR, and I'll end up with a vector PR. But when you write it this way, it highlights something. When you're adding them, it's sort of like you can smash them together and the Q cancels out. You see PQ plus QR, oh, that's a PR. Now, subtraction then, well, you might like to think of subtraction as actually addition, but you're adding the negative vector. So if I want to go A minus the vector B, then I go, well, here's A, and there's negative B, and I'll add those two together. So I'll go A minus B, and there's my vector, A minus B. Now here's the interesting thing. Those two vectors become the diagonal of the parallelogram created by the vectors A and B, sometimes known as the parallelogram of forces. So there's AB. I could have done it as B plus A. You create a parallelogram. Right? Opposite sides are parallel. That diagonal was A plus B, but the other diagonal was A minus B. It could also be B minus A. It all depends on where is the head, where is the tail. Which one is it going to be? It's always head minus tail. Head minus tail. So multiplication of vectors by just a number then. What happens? It's just going to enlarge it. It's not going to do anything to the direction because the scalar doesn't have a direction. It just multiplies it. So if there's vector A, well that would be vector 2A. They're going in the same direction, they're parallel. It's just one's twice as long as the other. That would be minus a half A. It's half as long as the first one, but it's going in the other direction. And they're all, of course, parallel. All right, let's look at this question. We've got a triangle. We've named AB is going to be the vector A, and AC is the vector C. P and Q are midpoints, and R is a point such that the vector RC will be twice the vector BR. Okay, we're going to come up with an expression for BC and PQ in terms of A and C. How do I do it? I said, well look, yes, I have one vector where I can go from B to C. How else could I get there? Well, what I could do, I've written it sort of the other way around because it makes more sense to have the minus in the middle. But what I've really done is I've said, oh well, instead of going from B to C, how about I go from B to A and then A to C? I still end up in the same spot. Well, going from B to A is the negative of going from A to B, and then plus A to C. Head minus tail is another way of thinking about it. So you end up with C minus A without either way. But what I say is if you think about it as head minus tail, you'll notice these two vectors are both coming from A, and it's creating this new vector. So all I've got to do is, well, if they're coming from the same way, what was this vector minus what was this vector? Head minus tail. C minus A. PQ, how can I work that one out? Well, okay, I want to go from P to Q. Another way I could do that is I could go, well, that's half of AB, P was the midpoint, remember? and then I'll add on half of AC. I'll end up with a half of C minus A. Compare those two. Okay. PQ is actually a half of the vector BC. Now this is where we now become a little bit different to physics. Some of you have seen these ideas in physics, but now in maths we turn it back into maths and geometry. Well, what property of a triangle have we just demonstrated? And what we've just done is that the line joining the midpoints of two sides of any triangle is going to be parallel to the third side. Because what we've just said is PQ is a half of BC. A half, that's just a scalar. So these vectors, if they're equal, they must be parallel. So we've got PQ being parallel to BC. Now sometimes we can prove geometric properties. Instead of using geometry, we use vectors. Right, how about we express BR and RC in terms of A and C? How can I get BR? So BR, well they told me that RC is twice BR. Now what ratio have we just cut that in? Well that means one part is BR, RC is 2 parts, so therefore BC must be 3 parts. So BR must be 1/3 of BC. And BC we worked out was C minus A, so we got 1/3 of C minus A. How about RC then? Well RC was 2 parts, we just said before, so 2/3 of BC, it'll be 2/3 of C minus A. We're now going to show that AR, so to get from A to R, we could go 1/3 of 2A plus C. I want to rewrite AR then. What's another way I can get from A to R using things I already know? And so to get from A to R, I could write it like this, because this is one of these ones I could go and smash it together. So I know it would be AB plus BR, and we found expressions for both of those. Well, they told us AB was A. We just worked out BR was 1/3 of C minus A, playing with algebra, and we have an expression for it, 1/3 of 2A plus C, which is what they wanted us to show. So that's just a little introduction on the fun that we have ahead of us.